That's Anderson Cooper, because this past weekend, the television show 60 Minutes had a feature on all of the things that were going on in this air taxi, they call it. They've even got this one painted yellow, like an old yellow taxi. And there are so many companies, probably at least 6 to 10 significant companies with many employees. And you can see Beta's won almost $400 million in just the latest funding round. Archer is another one out in California. Eve Air. Here's from the Vertical Flight Society. They even have a periodic, a newsletter called Electric VTOL News. And here they have another good link, top 10 eVTOL articles in 2021. And, you know, you can see all the different categories, and there's an eVTOL aircraft directory. And check out the numbers of different configurations and all over the world, right? Trying to make this work. Some of them, again, have gotten very substantial venture capital and corporate investments from the likes of Hyundai and Toyota and Amazon and so forth. Some of them are fledgling companies, but we all share a vehicle that is electric in mind, and we're trying to make something of that. So Kiran's position is now Senior Vice President at FEV's North American Technical Center outside of Detroit, Michigan, and Auburn Hills. His particular responsibilities include drivetrain development, e-mobility, and vehicle engineering. And he's involved since he graduated, which I think was 1995. Kiran was my first PhD student back in 1995 and was co-advised with my colleague George at Lissert and I. He worked on elastomeric material dampers and the material modeling for helicopter applications. So he got involved with noise and vibration materials and structural dynamics a long time back. He's done engineering work, management, and certainly leadership positions, as you can see, in areas of noise and vibration. H is handling.
Harshness.
Harshness, yes. I couldn't quite put my finger on harshness, noise, vibration, and harshness. Control, powertrains, and a number of different vehicle integration issues. He has a bachelor's degree in mechanical engineering from the College of Engineering at Pune, India. So he came to us from overseas, was a teaching assistant, a research assistant. He was my first TA also, my first class, aerospace structures back in the day. So with that background, thanks for indulging me for a few minutes here. And I think we have a good attendance right now. So let me stop sharing and hand the ball over to Kiran.
Yeah, thank you, Dr. Smith, for the kind and warm introduction. I mean, for me, it's a great feeling to come back. It's just like coming back home. So thank you. And yeah, I see George there. Hi, George. Good to see you. And I'm really, I owe a lot to both of you for taking care of me during my Penn State days, and I'm really happy to be back here. So let me share my screen. Hopefully you can see my screen and we can get the slideshow going. Can you all see my screen, first of all?
Yes, I can see it.
I just need to start the slideshow, and all the normal PowerPoint buttons are hidden, but hopefully this is okay.
That worked great.
Okay, let me get my laser pointer. Yeah, thank you again. So I'm glad to be here. I'll give you a little bit of a glimpse into the world of NVH in the automotive industry, and with a focus on e-mobility or electric vehicles. So NVH is a Detroit buzzword. So it stands for noise, vibration, and harshness. It's really structural dynamics and acoustics in the vehicle is all it comes down to. but it's a buzzword that yeah, I hadn't really heard much of in my Penn State days, but certainly it's very popular in the automotive circles. So that said, let me take you through my planned agenda, and I have a lot of slides, so I'll maybe fly through it in the interest of making some time to have a discussion at the end. So I'll give you a little bit of context into what FEV does and where I fit in, to hopefully provide a little bit of reference to the rest of the slides. Talk a little bit about global automotive market trends, and then get into the development process for EDU, it's the electric drive unit, from an NVH perspective. Show you a couple of examples of EDUs that are in development at FEV. Talk about some test-based EDU methodologies for NVH and vehicle integration, and then a brief summary and hopefully enough time for a Q&A. So I have more slides than I can do justice to in a 45-minute session. So I'll fly through it in the interest of making some time for a discussion. So a little bit about FEV. So FEV is a global consulting company. So let me see if I can minimize the screens here. That's better. Okay. So we're a global consulting company, engineering service company. So headquartered in Aachen, Germany. It's a spin-off from the Aachen Technical University, which is where the company grew out of in the late 70s. And it's a family-owned consulting company that has grown since then, with technical centers all over the world. The big ones in Germany, in Auburn Hills, Detroit, where I'm located. Sao Paulo, Brazil, Puebla, Mexico, Pune, India, and in Beijing, China. Those are the big ones, but we definitely are globally connected to all of our customers. 6,500 employees in the global FEV family. So we work for a variety of industries and customers. It includes working with universities in many cases, working with startups, which is happening more and more, especially in the e-mobility area. We work with the regulatory bodies, EPA and its Department of Energy, etc. Many OEMs, many suppliers. So fundamentally, we are not connected to any one industry or one company. So it's the transportation industry that we serve in different capacities. So this slide gives you a feel for the breadth of our services. So vehicle development includes all aspects of full vehicle development. And I do have one slide on that. I'll get into some details there. Powertrain is everything from conventional IC engines to electrified propulsion systems and everything in between. Intelligent mobility is an area that is also fairly big for us. This includes autonomous vehicle development, all levels of autonomy, cybersecurity, functional safety, and software development, and big data analytics. So all that falls into this space. We're also heavily getting into the energy space. That includes the energy infrastructure, but also all the alternative forms of energy, as shown here. Software and testing solutions is the only group where we actually develop products. There could be software products for calibration, simulation, etc. But also we get into development of full test cells for testing components of full vehicles, where we take on the design and development and commissioning of test cells for many of our customers. And consulting is a strategic consulting group that offers business consulting to our customers, but draws on the technical know-how from all the technical areas you see on the left. So that's a very high-level view of FEV. So in the e-mobility space, and in particular, what we mean by e-mobility is development of electric drive units, or EDUs. That's the way we call them. Fuel cells, which is also part of the e-mobility space. Definitely battery development and integration of all these components to vehicles. And it doesn't matter what the vehicles are. They could be motorcycles, it could be passenger cars, Class 8 trucks, tractors, construction machines, and like Dr. Smith, you mentioned also eVTOL aircraft. So we're connected to all the, let's say, all the end customers, but fundamentally it's these kinds of components that are designed and developed for integration in these vehicles. In the vehicle engineering space, FEV has grown significantly for, let's say, full vehicle development. That includes everything from vehicle architecture and concepting to developing the chassis, suspensions, and the EE architecture, body in white development, exterior, interior, the lighting development, which is also an interesting area, and also vehicle attributes. And I'll come to the attributes in a second, because this is where NVH fits in, supporting our customers all the way through production. So when they talk about attributes, it is essentially doing all the CAE, or simulation-based work, or the test-based work to support development of attributes like aerodynamics, efficiency, which is connected to range, thermal management, which is very important, especially for battery electric vehicles, active passive safety, dynamics, durability, and last but not least, NVH. So all these are important attributes which we support initially through CAE and simulation-based methodologies, and certainly later through testing. So with that, I want to give you a very brief overview of how we see the market evolving globally. So this is a snapshot that comes from our consulting group, strategic consulting group. We call this a moderate transformation scenario. What this means is that no one knows the future, so there's different scenarios that are modeled. And we have an aggressive scenario and a moderate scenario in terms of electrification. And this is one scenario. And these models are informed by all aspects that are important in defining this future landscape. So everything from the cost of fuel to the maturity of battery technology, cost of batteries, cell chemistry, customer preference, regulations, all of these things go into developing these scenarios to define what the future of the automotive industry might look like. Long story short, we see growth happening across the globe. We think the mature markets like Europe, US, Japan, South Korea, etc., will stabilize after 2025, but there is definitely increase happening in the emerging market and China. So that's where the overall growth happens. We see a reduction in the ICE-based powertrains on the order of 32% from 2019 to 2040. So significant drop in ICE or internal combustion engine-based powertrains. And that drop is taken up by BEVs, or battery electric vehicles, as you can see here. We also see a small space for fuel cell vehicles. This initial growth will happen in South Korea and Japan, based on where the market is heading, but they're small markets relatively. So for it to gain more traction, it needs more time because of infrastructure as well as cost-related issues. So the main message here is that you'll see a lot of electrification in the automotive market. If you look at the US market, and again, focus on this moderate transformation scenario, we think by the end of the decade, so 2030, there'll be 20% battery electric vehicles and a variety of hybrids. So you can see it's everything from plug-in hybrids to micro to mild and strong hybrids. I don't have enough time in this presentation to go through all the definitions, but I'm more than happy to talk about this in the Q&A if there's questions. But we think that electrification is happening in a big way, but there'll be a lot of hybridization before the transition to full electric vehicles in the US market, driven by a variety of reasons, regulations, government policies, customer acceptance, which includes cost, range anxiety, things like that, all that play into this. So there is a space for hybrid vehicles, and the hybridization all happens within the transmission. There is different kinds of hybrids, series and parallel hybrids, and many kinds of parallel hybrid architectures, P1, P2, P3, etc. Without getting into all the details, all of them use electric machines in different parts of the drivetrain, but electric drive units are going to be very important for battery electric vehicles for sure, but also what we call P4 hybrid applications. If you can imagine an all-wheel drive vehicle where the front axle is driven by a conventional IC engine-based powertrain, and the rear axle is driven electrically, that offers all-wheel drive capacity, and that is a P4 hybrid architecture, which also uses an electric drive unit. Range extenders, very similar configuration, but it's an electric vehicle with an ICE-based genset. And lastly, fuel cell electric vehicles, which will also need electric drive units. So the main message here is that the electric drive unit market will grow exponentially, as you can see here, and that's the focus of this presentation, looking at it more from an NVH perspective. So if you look at integration of electric drive units into vehicles and development of battery electric vehicles, these are all the kinds of attributes that come into play. I won't go through all of them, but suffice it to say that NVH is a very important attribute. And it's not the only one, and oftentimes it's a trade-off between NVH needs and many other needs, such as dynamics and performance efficiency, etc. They're all important, but at the end of the day, from a customer perspective, NVH tends to be very important. And that's where a lot of focus is happening and will continue to happen to make sure that these vehicles are customer friendly at the end of the day. So what's the key difference between ICE-based vehicles and battery electric vehicles? If you look at the pie chart here and look at overall noise levels inside the vehicle, the share of powertrain noise is very significant for ICE-based powertrains, and then you have smaller shares for road noise, wind noise, and noise from other auxiliaries. For a battery electric vehicle, the pie chart looks different. You do have road and wind noise being dominant from an overall level perspective, but certainly powertrain is also an important source, although not the most dominant source in terms of levels. That said, the importance of powertrains from a noise perspective is more in the area of sound quality, because electric drive units, both the geartrain as well as electric machines, they do emit high frequency noise. And this tonal character is something that's very hard for customers to accept in the vehicles. So it's more of a sound quality issue that needs to be addressed. And I'll show you how we address that and how we are trying to tackle those challenges. But also active sound design has a role to play, and I'll show you a couple of examples later in the presentation on how that can be incorporated in conjunction with passive technologies. So if you look at road and wind noise, so the scatter band here, the gray band, which is what we call a scatter band in FEV terminology, comes from a database of vehicles we've tested. If you look at the road and wind noise contributions, typically they fall within the scatter band, so as a function of vehicle speed. So if you look at the noise induced by the electric drive unit inside the vehicle, if you happen to be in this red range where you're in the middle of the scatter band of road and wind noise, that's a problem because it's going to be very dominant and it's going to cause a concern with the customers. On the other hand, if you're at the bottom of the scatter band, then it's acceptable, but it might be disturbing or annoying, which needs to be addressed in specific speed areas or specific frequencies. And certainly if you are 5 dB below the scatter band, then it's barely audible, which is what you'd like to be, but it's not always achievable. So there are sound quality metrics like tonality targets that define how high can the tonal noise be above the masking noise that comes from wind and road noise for most part. And you have to define what's called a masking noise surface and define targets for what is acceptable from a tonality noise perspective from an electric drive unit. Once you define that, then you can start breaking this down into what could be permissible airborne noise share inside the vehicle coming from the electric drive unit and what is permissible structural noise share. And you can further break it down into the various subcomponents. But at the end of the day, the goal here is to define the target at the vehicle level in terms of what the driver's ear measures, so to speak, or what the driver listens to. And then you break it down through a very structured process into what is acceptable in an electric drive unit as tested in the component test cell, in a semi-anechoic test cell. So that's the process here to define targets that at the end of the day, if you meet those targets at the component level, then you can have reasonable confidence that it will work in the vehicle. So there is a lot of initial concept design work that needs to happen to meet those targets, including separating orders to make sure that you don't have an interaction between the gear train orders and the motor orders, etc. How do you mount the electric drive unit to the vehicle? There's considerations that go into play there, and I'll share some examples. And then certainly FEA-based analysis for both the structural dynamics as well as electromagnetic analysis. And then you couple them to get the influence of electromagnetic forcing and gear train forcing to look at the overall system and then predict the surface velocity or radiated noise. And I'll show you a couple of examples here. So FEV, we use a tool called Virtual Dynamics. This is actually developed by us, by FEV, and sold as a commercial product. But it's really, think of it as an application that runs on top of Adams, which is the industry standard made by MSC. So Adams is a solver, and Virtual Dynamics is an application that is more powertrain, drivetrain centric. That's developed and sold by FEV, but it runs on the Adams solver. So in this case, this is an example of a hybrid transmission, so electric machine here, and it's an automated manual transmission. An automated manual transmission is one where if you go through a shift, which happens automatically, you go through what's called a torque hole. So the shift quality is very, very hard and not acceptable to customers. So the idea here is to introduce an electric machine to fill the torque during the torque holes to provide smooth shifts, but at the same time to offer electric drive and full hybrid transmission potential. So in this case, we were looking at the influence of this combined system and trying to understand the noise of the whole drive unit. So using Virtual Dynamics, which is a multi-body systems-based tool, but bringing in the flexible, let's say, structures through finite element analysis to look at this combined MBS, FEA, let's say, approach. And then once you do this, then you're able to look at the baseline configuration and predict, in this case, acceleration, as shown by the sensor here, what we're predicting. And then if you look at the modifying the microgeometry, looking at tip relief, lead crowning, and things of that nature to modify the microgeometry to satisfy noise needs, then you can simulate this and look at the influence on noise. And the correlation is reasonably good, I would say. It's not perfect, but it's reasonably good, enough to give us direction to make sure that we have confidence in the gear layout and the microgeometry design. This is one example of a hybrid transmission. And this is an example of an electric drive unit where we do very much similar analysis initially through FEA, and then we bring in the multi-body systems analysis to combine FEA together with MBS. And then with Virtual Dynamics, since it runs on the Adams platform, there's a plugin to work with Actran, which is acoustic finite elements. And in the end, you're able to get the influence of electromagnetic forcing and gear train forcing and do a forced response analysis and predict the overall noise signature 1 meter away from the electric drive unit as an example. You can get sound pressure, sound power predictions, and look at the influence of the excitation of different resonances or natural modes of the system, which might need to be addressed depending on what the masking noise is from the other sources like wind and road noise for when a given frequency might get excited. So this kind of analysis is important to optimize the NVH behavior of drive units. So I'll show you a couple of electric drive unit examples to give you a feel for the internals. So this is an example from a light commercial vehicle, as you can see here. It's 2 electric machines going through a common differential through a beam axle. So this is scalable, but this architecture is what's more important. And I'll show you a brief animation here that shows you what the internals look like. So in this particular case, we use identical electric machines because of cost and packaging reasons, and they go through a common differential to the output shaft. So it's a very simple architecture, single ratio. So as you can see, from an NVH perspective, it's important to get the electromagnetic forcing understood, the geartrain forcing understood, and then you know how to optimize the housing structure. So that's a simple electric drive unit from a vehicle application for a light commercial vehicle. And this is an example of a more advanced application. This is a 2-speed EDU. It's a planetary gear set-based system for an off-axis design that could be used in a medium-duty vehicle or a performance car. And again, it's scalable. And I'll show you a brief animation here to show what the internals look like. So that's the electric machine. This is an axial flux machine, which is very package friendly for this architecture. And this is the internals of the gear train. You'll see in a minute. So these are examples of FEV designs as part of our internal R&D. And we use this to get our customers interested to see if they have an interest in these kinds of technologies. So that's the planetary gear set-based system with the clutch packs and brakes. Not different from, let's say, automatic transmissions that we may be used to. But this is a pure electric drive system with two speeds. You see the park lock system here and the transfer gear to the differential. So all these systems essentially need to be analyzed using MBS and FEA to make sure that we analyze all the mechanisms that might cause noise. And then we get into a test-based development process. So from a testing perspective, we typically put these electric drive units in a test cell, and we break the noise down. First of all, we look at the overall noise levels, and then we break it down into mechanical noise and electromagnetic noise. And this is the process which we call EDSL. It stands for electric drive sound level. It's an acronym, but really it's a breakdown of the noise into mechanical noise, electromagnetic noise, and then a further breakdown to understand what the order content is coming from various gear train elements, and what the order content is coming from the electric machine and the inverter. So these kinds of breakdowns are useful, as you'll see here. This is the typical test setup in a hemi-anechoic test cell. And we have, we test these machines under very prescribed speed and load profiles. The first step is to look at the overall noise itself to make sure that it's within the scatter band of overall noise levels from other electric drive units. That's the first step, but it's not enough. If you're in the box, it means that you have a good starting point. It doesn't mean that it's good enough for a particular application. So the next step then is to do something like this. For each microphone, we look at all the orders and break it down into what might be coming from different sources. So all the red orders here, it's kind of hard to see, but the ones that are tagged in red are electromagnetic forcing orders from the electric machine. The ones in green, the fan you see here, comes from the inverter and the power electronics. The switching frequency is at 8 kilohertz for this particular machine. And you see that here. And then you see the mechanical orders, which is shown in orange. This comes from various elements of the gear train you saw. So once you do a breakdown like this, then the next step is to break it down into the overall summation of electromagnetic forcing orders, mechanical orders, switching orders, and remaining broadband mechanical noise. So we do this, and then we compare this to our scatter band from the industry to see if a particular EDU for each of these, let's say, subcomponents is also within the box or not. If it is not, then it signifies that there may be an area for focus for improvement, and then that allows us to focus our testing and simulation activities to improve the characteristics in certain speed and frequency ranges. Then at the end of the day, we develop these maps. The 3D map, the x-axis is speed, the y-axis is torque, and the color axis is really the noise levels. So the idea here is to make sure that all the subcomponents of noise, they have smooth transitions when you go up the speed and load, such that you don't have any abrupt increase. This might seem very abrupt and objectionable to the driver of the vehicle. You don't want that. So the idea is to smooth things out and make sure that you have a smooth increase in all the noise shares, such that the overall integration then in the vehicle can be more smooth. So from a vehicle integration perspective, mounting of the EDU is very important. So there are many architectures, but the most common ones are a 3-point mount or a 4-point mount. We're using elastomeric mounting systems. But it's also important to understand how it is mounted. And then once we've done that, it's also important to understand the resonances within the mounts themselves, because they can amplify the higher frequency noise. So from a mounting perspective, you can have a one-stage isolation concept, which is fairly common also in the conventional powertrains, or a two-stage isolation where the electric drive unit is mounted to a subframe, which is isolated to the subframe, and the subframe itself has another layer of isolation to the vehicle. So this is more common, but with this, you have to be very careful that the rigid body modes, so when you have the rigid body of the electric drive unit on the subframe and the subframe on the basic vehicle body or frame, these kinds of rigid body modes need to be properly decoupled to make sure that they're not amplifying each other. And if done properly, then you have more potential for high isolation with a two-stage mounting system in the higher frequencies. And this becomes important for electric drive units because of the high frequency nature of the forcing functions. And then we have this powertrain mount design tool. It's a MATLAB-based tool. But the idea here is to then specify the mount locations and the stiffnesses and newtons per millimeter in the X, Y, Z directions. And then you can use sliding bars to move things around and then understand if you're meeting the various metrics in terms of the overall motion of the EDU during different maneuvers, and also decoupling of all the rigid body modes, pitch, yaw, bounce, etc., to make sure that they're properly isolated from each other. And we can also get an initial impression of what the noise could be in the vehicle based on a certain mounting architecture. So this is the first step. And at the end of this, we define what the mount force reflection curve needs to look like, both in the linear range as well as in the nonlinear snubber range, where you want it to actually hold the EDU from deflecting too much so that it doesn't crash into the vehicle frame rails. So having done this, then we get into the vehicle, let's say, integration from a test perspective. And then in this case, we use a noise transfer path analysis. This is done in the time domain, and we call it VINS, VINS, which stands for Vehicle Interior Noise Simulation. At the end of the day, what we're trying to do here is to instrument the vehicle with microphones and then understand microphones and accelerometers at the mounting points and understand the source of the inputs going into the vehicle. And then we also have transfer functions characterizing the airborne path, or the P over P as we call it. So we use a speaker and do this reciprocally. So we have a speaker inside the vehicle in the driver's seat location, and then we blast white noise essentially, and then measure the response at different locations on the hood. And then we're able to characterize what we call as P over P to get the acoustic transfer function from that path, or those paths. And likewise, with the same thing on the structure bone side, where we're looking at the what's called A over F, the inertance. So basically, it's going to impact hammer to impact the location of where the electric drive unit mounts into the vehicle, and you get that function. At the same time, you measure the P over F function, which is the sound pressure response in response to a unit force input at the mounting point in the vehicle. These kinds of transfer functions, once they're available, then you can combine them with the source measurements to actually predict the noise inside the vehicle, simulate the noise inside the vehicle. And you can also measure this to do some correlation work initially to gain confidence in the model. Once the confidence is established, then you can break it down into the airborne share, structure borne share, and break it down into what's coming from each side. So the airborne share, what's coming from the top, front, bottom, left, right, etc. And if you have a 3-point mounting system, then you have 3 mounts, 3 directions. So there's 9 structure borne paths. All of these then contribute to the structure borne noise share. And then all of this sums up into the overall noise at the driver's ear. All this is done in the time domain, so you can listen to it and also get a subjective feel for where the issues might be. and what might need to be fixed by understanding the noise mechanism that might be causing this issue. So this is electric drive unit induced noise. And then once you do this right, then you're able to understand the influence of mount isolation on the structure bones path, the influence of local dynamic stiffness, and or the vibroacoustic transfer function, or the P over F, as we call it. So if there's an issue with structure bone noise as seen here, then it could be perhaps because the mount isolation is not good enough, or maybe it's because the dynamic stiffness is not high enough at the attachment point, or maybe because the vibroacoustic transfer function has some weaknesses. So again, each of these needs to be looked at clinically, so you can target the improvements in the right areas. A little bit about road noise. It's very similar to powertrain noise, but a little more complicated. So in this case, we cannot look at each path separately because of all the suspension bushings, all being similar to engine mounts or electric drive unit mounts, but they're much stiffer. Because they're much stiffer, there's more cross coupling between different paths. So you end up with an inertance matrix then instead of single functions that needs to be inverted to obtain forces at various points where the suspension attaches into the vehicle structure. And then you do some analysis where you then multiply the force by the P over F to get the noise share from each suspension path. And then you get maps like these that you can look at to see where the issues might be and understand the noise mechanisms. And then you see what needs to be done from a tuning perspective. So that's another process which we call chassis VINs, very similar to the previous electric drive unit VINs, but this is more focused on road noise. The next topic, which is important for electric vehicles, is what's called AVAS or AVAS. It stands for Acoustic Vehicle Alert Systems. So there is a requirement from NHTSA, from FMVSS, Federal Motor Vehicle Safety Standards, requirement for the noise of an electric vehicle to be loud enough such that it can be heard by pedestrians and specifically blind pedestrians. So the idea is to make sure that they are alerted of an electric vehicle that might be approaching at low speeds, and the idea is to have it emit enough noise such that they can be alerted and we don't have an accident. So that's the premise. And there's actually a requirement now that this needs to be integrated into electric vehicles. So this is done through speakers. There's typically a speaker at the front of the vehicle that emits noise. But as you can imagine, it needs to be loud enough to meet the requirements from an FMVSS perspective, but it cannot be so loud that it distorts the NVH inside the vehicle. So it has to be done very carefully. So we have a process like this where we measure these transfer functions. In this case, we have a loudspeaker sitting outside here to be at a pedestrian location. And then we'll look at the response of the loudspeaker noise to what's measured inside the vehicle at the driver's location, as well as the speaker location where the speaker for the acoustic vehicle alert system is located. So these are the transfer functions we need to measure. Then we go through the strap maneuver and actually go through the speed trap and measure the noise at the various locations that need to be met. And then we measure the noise at the source of this AVAS speaker. And then once we've done that, then we're able to actually synthesize the audio inside the vehicle and outside the vehicle. And then the idea then is to optimize the noise such that it is loud enough on the outside to meet the requirements from a Federal Motor Vehicle Standards safety requirements perspective, but not so loud that it causes issues inside the vehicle. So it's a very delicate balance. And so we measure these transfer functions. So this is a typical transfer function between the speaker location to the driver's interior. You can see here you have to be as low as possible. So lower is better. That way you're minimizing the inputs from the speaker into the vehicle. And this is an example of transfer functions from the speaker to the pedestrian locations. So here you want to be as high as possible. So this is front left speaker, front right speaker, etc., showing different speaker locations. The x-axis is frequency, and the y-axis here is actually an angular location around the vehicle. So we're looking at pedestrians around the vehicle, with this being the front and this being the sides essentially. So with this, we're able to optimize the location of the speakers, and then you can optimize what the sound file from the speaker needs to sound like to basically meet the requirements on the outside, but not be too obtrusive on the inside of the vehicle. And so this is an example. So if the vehicle going through a typical speed profile from 0 kilometers per hour to 25 to 30 kilometers per hour, and then a coast down back to 0. So in something like this, you want your sound profile to also be similar. From your speaker, you want it to go up with vehicle speed and then go down with vehicle speed, so it's more natural to the external pedestrian. And so this is this color map here shows our synthesis of the speaker, AVAS speaker induced noise inside the vehicle. And this is how it sounds on the outside. So once you have done this, then you can work with tools like these to maximize what the noise on the outside needs to sound like and be like to meet the requirements. But also you want to minimize what's heard by the driver inside the vehicle, so they're also comfortable. So it's a delicate balance, but we have structured processes to meet these needs. And then maybe a couple thoughts about active sound design and how that fits in. So when I say active sound design, here we're talking about actually using the speaker inside the vehicle, the radio speaker, to actually pipe in sound that might not be existing initially. So it's actively designed and added. And if you do this right, then you can actually mask the noise from the AVAS system with artificial sound coming from the speaker, which the driver or passenger of the vehicle would be completely oblivious to. So they wouldn't even know about this, but it's happening actively. And this noise here can mask the AVAS noise such that you're able to meet the AVAS noise requirements without it being obtrusive inside the vehicle. But again, this has to be done carefully in a way that doesn't make this objectionable inside the vehicle. But this is the first step that can be done from an active sound design perspective. The second step then is to take it one step further, where you're not just masking the AVAS speaker noise at low speeds, but you're actually linking this to the driving condition of the vehicle. So depending on the pedal torque demand from the driver, you're able to increase the noise coming from the speakers, which would seem like it's naturally coming from the electric drive unit, but it's not. It's meant to provide some acoustic feedback to the customer, because with electric vehicles, we have high torque at low speeds. So the driving performance is very good, but it doesn't match the acoustic expectation from what they expect it to sound like in the vehicle, especially when they're accelerating. So you can do this artificially by piping in noise through the speaker system actively, but have it linked to the vehicle CAN bus, have it linked to the electric drive unit's speed and torque information, such that it matches the driving profile from the customer if they're coasting down or accelerating or cruising. So you can design it to be more natural to the customer. So with that brief summary, hopefully I was able to give you at a very high level, at least, the challenges and opportunities presented by electric vehicles from an NVH perspective. There are many good processes available from a CAE simulation perspective, as well as test-based methodologies. They're currently available and being used by the industry. So if used properly, then this process can be fairly smooth, and you can design you can develop and design a vehicle that at the end of the day, the customers can also find to be very, very appealing to them, which at the end of the day is one of the reasons for one of the requirements for the vehicle sales to go up, to increase the share of electric vehicles in any given market. So with that, I'll stop my presentation. I'm happy to engage in a discussion.
Thanks very much, Kiran. That's a great overview into a field that we're not specifically familiar with yet, but I think there's growing interest. A lot of the tools you mentioned are probably familiar to much of this audience, as far as acoustic finite elements and transfer functions, and but you've got a very experienced group of engineers working for you, clearly. So
yeah, no, thank you. So it's no different with any vehicle, right? If you're looking at eVTOL, I think it's very similar. Of course, the forcing functions are different. They need to take into account not road noise, but certainly aeroacoustics and noise from the rotorcraft, in addition to what's coming from the drive unit itself. But the process, I can imagine, is very similar.
Well, I think it's in its infancy compared to what you guys are doing in the automotive field. You know, the eVTOL NVH is something that we'd like to get out ahead of. A lot of people are working to get the aircraft off the ground and flying the range, and with the safety, those other vehicle attributes, with the cost effectiveness. But it's a bit of a mystery what they sound like inside to the occupants. We just know that conventional turbine engine helicopters are extremely loud. Yes, as you can imagine. So that's a whole nother non-EV question, this is very interesting to us. I know I'm keen to follow up with you, and see what we can learn.
Absolutely.
Open the floor to any questions. It looks like we have about 20 people in the virtual audience. So I will pipe down and let someone else ask you some questions.
I'll ask a question.
Hi, Andrew.
Hi, Kiran. So I'm curious on your thoughts on AVAS systems and community noise. We've kind of got ourselves in an NVH world into a position where our vehicles are so quiet that we're generating noise, especially in big cities where you have a lot of these vehicles. Is anybody thinking about how these sounds sum up over a quantity of vehicles?
Yeah. Especially in Europe, I think there's more of a concern. They have very strict pass-by noise requirements from a community noise perspective. And so they've spent a lot of time trying to minimize noise at higher speeds. So road noise is in particular, it's very, very important to lower road noise at high speeds. So there's a lot of activity going on there. But the AVAS speaker noise is really at low speeds. I'm talking from 0 to 20 miles per hour, that range. So that's an area where there is not much noise from conventional vehicles. And so this is almost deemed necessary. So this was, in fact, a pedestrian for a consortium for blind pedestrians, if you want to call it that was lobbying with the Congress more than a decade ago to actually make it happen. So the auto OEMs did not want this, obviously, but they're being forced into this because of safety concerns. And we've done some experiments actually where we've driven conventional vehicles and EVs at low speeds to understand how much of a difference there is. And there's more than a 10 dB difference for, from a pedestrian perspective. So it is really conceivable that you might, if you're a visually challenged pedestrian, that you might not hear an EV coming at you at low speeds.
Yeah, as a runner, I can confirm that you can't hear even hybrids sometimes at low speeds. Well, they are electric at low speeds. So.
Exactly. So it's a real concern.
I think Andrew's question, as far as I heard it, was if you have all of these dozens of dozens of electric automotive vehicles on the street, actively making sound to warn dozens of pedestrians, then there's kind of a new noise source in the street, right? From all these cars kind of alerting all of these pedestrians. Is that the?
Yeah, and I don't think it's necessarily a level issue, but it's possibly an annoyance issue for the people that live nearby, right? If you're in a city in a high rise, 3 stories above an intersection, you're gonna be hearing that all day long, which is an interesting thing to think about.
The idea there is to not make it any worse than a conventional IC engine vehicle, right?
Yeah.
So it won't be any louder, it won't be any more annoying, and certainly OEMs, they would also use this to craft the DNA of the vehicle. They don't want it to be annoying. And so it can be made pleasant and low enough to meet the requirements, but not high enough to be a problem.
Could you make it sound like an old VW Beetle?
You can. You can. And in fact, we did some studies where we actually used artificial noise. This is not for the outside, but the inside.
Oh,
We made it sound like an i4 engine and a V6 engine and made it sound very sporty. And we did a jury study. And what people found was that they did not like the fact that we were trying to make EV sound like an IC engine vehicle. They did not like that. However, they appreciated the acoustic feedback because with an EV, if you do nothing and you hit the not the gas pedal, but I'm going to use the word gas pedal. If you hit the gas accelerator pedal, it throws you back and you accelerate in a very nice way because of the torque characteristic of the electric motor. But there is no acoustic feedback, so it's very surreal. And so adding some noise actually is not a bad thing from that perspective.
So you might have mentioned this already. I'll ask a quick question. Are you looking at the use of active mounts, or do they tend to be, they are active? Okay.
Yes. Not so much for electric vehicles, because the electric vehicle, let's say, issues a more high frequency structure borne noise. I'm talking, more than 1,000 hertz. But active mounts are more, they're used with hybrids and conventional IC engine based vehicles, which are, when you look at cylinder deactivation as an example, right? or start-stop. And you look at things like that, which is happening naturally to minimize fuel consumption, then active mounts are used to actively cancel out the force inputs into the vehicle.
Is
So-
there, I guess, I don't, without naming names of products or companies or OEMs, is there a noticeable difference in the interior NVH or noise in particular environment from one electric vehicle to the other? I haven't been in enough of them to, but I know on wind noise, for example, there are definitely some vehicles that are louder.
Yeah.
And some of the high-end vehicles put a lot of effort into reducing or minimizing these the cabin noise. So,
No, exactly. There's differences. There's differences because road noise, wind noise, and powertrain noise are three main sources. So with road and wind, yeah, certainly there's lots of differences, and it influences noise levels, but it doesn't add character, right? It's broadband, random noise. So it doesn't add any nice character inside the vehicle. So that's where the differences are. But if you look at a luxury vehicle as an example, as opposed to an entry-level vehicle, right? If you look at these two segments, the luxury vehicle, there's a lot of effort spent with the sound package to minimize the road and wind noise inside the vehicle. So once you do that, the masking noise goes down to a point where the powertrain becomes more dominant. And that becomes a problem. So that's where that balance again needs to be struck carefully. But to answer your first question, yes, there are differences between the different OEMs, and it really comes down to balancing these three noise sources.
how about within the EDU generated noise itself, right? Are there, if you take out the road and wind noise, as best you can, like you're a trained ear and your colleagues, you can probably hear exactly what's going on.
Yeah, you're absolutely right. Even there, it comes down to the geartrain noise, right? So if you look at the geartrain, it's where do companies want to spend their money? Some companies spend their money on gear manufacturing and microgeometry, which tends to be very expensive. And some other companies actually do this from the ground up, where they design the force inputs of the bearings from the geartrain to be as low as possible, right? And so we're doing a lot of benchmarking studies right now where we do an initial, let's say, noise measurement of the EDU in the test cell. And then we reverse engineer that and actually model the EDU one by one, component by component, and build it up to do a correlation and then understand where did company A spend their money? Did they spend their money on the microgeometry enhancements, or did they spend their money on the architecture up front to minimize inputs going into the EDU, right? So these kinds of questions are being asked by our customers, and we are in the middle of doing exactly that.
Interesting stuff.
So
We're way behind you. eVTOL, like I said, we're just trying to get off the ground and stay off the ground.
and another area is the inverter noise, which comes from power electronics. So the typical switching frequencies for the inverters are in the 5 to 8 kilohertz range. And so definitely in the audible range. So if not properly managed, these frequencies can also excite the natural modes of the housings of the EDUs. So I'm talking 5-6 kilohertz, and that becomes a problem. And so the industry, from an NVH perspective, is pushing the switching frequency to be higher and higher. But then there's a trade-off with efficiency, which impacts range. So and then the thermal management aspects that come into play. So there's a lot of trade-offs that need to happen, and there's lots of fights that happen in the conference rooms till they reach the happy mediums.
All right. Well, the Nittany Lions usually know we can fight.
That's right. That is right.
I have a question, if I may.
Please.
Thank you for this very good overview. When I was riding in an electric car, the only electric car I know was a Tesla, and it was a rather old one. And I found out that if I'm not going very fast, I just don't hear anything from the powertrain. And if I'm going faster on a highway, I hear even more wind noise than I would
Yes.
here in my 15-year-old car,
Mhm.
which is an ICE. But this is just one experience I had. So I figure that if you're on low speed,
Mhm.
you actually don't hear anything, almost anything of the powertrain, and you may hear some noise you never heard before in the car, like, I don't know, squeaking of the seat or
Yeah.
something like this. So I was wondering, what are the main challenges in low and in high speed if you go on a electric car, especially when you think of low speed where there's no wind noise, there's obviously almost no driving noise,
Mhm.
but there's noise that you haven't heard before in
Yeah.
an ICE car. So I was wondering, what are your main challenges then that are left actually in the cabin
Yeah.
for a driver in these electric vehicles?
Yeah, no, very good question. So the low speeds, you certainly don't have wind noise. There is road noise at low speeds also, but maybe not as significant as high speeds. Surprisingly, you do pick up electric drive unit noise at low speeds. It starts with initial, what they call cogging. So, you have pulsations in the, let's say, torque output from the electric machine. This can cause cogging noise. You can also get rattle in the geartrain, etc., at low speeds. But that needs to be avoided by design. So that is an issue. But you also get the wind noise as it starts winding up as the electric motor speed goes up, right? If you look at electric machines these days, they spin up to 18, 20, 25,000 RPM, right? With a huge ratio, because you need a huge ratio for it to work, to be reasonable, the output shaft. At low vehicle speeds, the electric machine speed can be pretty high. And that can cause noise, which is more pronounced at the low speeds because the masking noise from wind and road noise is low. So that's one area. But the electric drive unit noise typically is not constant through the speed range. You see it go up and down, and that's because certain resonances are excited by the orders coming from the geartrain and the electric machine. So that needs to be understood, and you need to focus on these narrow zones, even in low speeds, where there may be issues. So that is one that's a concern. Now, the other concern, which we didn't talk about today, is noise from everything else. You're talking the HVAC blower fan noise from the from the AC system, right? The heating system. That can be very perceived as being very high, even though it is not, because you don't have an engine running, right? So any noise is perceived as being very high. So it's more of a perception issue, even though it's not a level issue, but that's a concern. Things like pumps, right? You might have cooling and heating pumps inside the vehicle as part of the HVAC system, as part of the lubrication system that come on and off on demand. And if that happens without noise from an IC engine, then you hear it. And so you have to be careful about not making that an obvious issue. And so how do you calibrate it, and how do you mount it in a way that doesn't introduce spurious noise in the vehicle? Those kinds of things are also important.
So it's rather like rattling noise and like high frequency noise, that if you have these RPMs, I mean, that's such a frequency that you never had in an ICE car before. So this might be then the new challenge. Okay, thank you.
Yeah, no problem. Are there any other questions? We have a few more minutes. I'm happy to answer.
Anything from our students in the audience? Normally, you can blame the pizza, for no questions. Students are chowing down on the pizza. But how about now? Can I challenge any of our students who might be in some of the courses, acoustics courses? They might want to ask Dr. Govindswamy how to solve your final exam take-home questions, coming up. So you can reach out to him. He was a fine instructor as well as a good researcher and a good colleague. So if there are no more questions, thanks very much for your time. I know it's valuable, Kiran. thoroughly enjoyable and got a lot of wheels turning in our mind as far as how we might want to work together with you in CAV and beyond. Thank you.
No, thank you very much. It's a pleasure for me to participate in this forum. So thank you for inviting me, and I look forward to future interactions. See you.
Yeah, Kiran,
Bye-bye.
that was very nice. Good to see you. Hope to see you in person before too long.
Absolutely, absolutely. I'll make it a point to come. But very nice to see you too, George. So thank you.
Thanks so much, Kiran.
See you then. Bye bye.
Thank you all.
All right.
Nice day.
Have a good evening in Europe. Yep.
Thank you.